So we continue from where we had stopped. Yesterday. And we were looking at what we called reliability tests. We are looking at what we called reliability tests. And these reliability tests, we are getting them from the question of April 2022. Question number 5. That's what we did the sheet for. And I said reliability tests are tests that we undertake to assure ourselves of how accurate the equation that we have developed is as a forecasting model. If you remember, I think we developed an equation yesterday, which was y is equal to, was it 854? Collins, remind me, it was what? Oh, I can see it. It was 2 that 1. The equation was 2 that 1 plus 12x. Plus 12x. That is the equation that we had. 2 that 1 plus 12x. Now, these tests are divided into 3 areas. The first area is called economic plausibility. The first area is called economic plausibility. Economic plausibility tests. And as you have seen in your notes, economic plausibility test is simply a test that we do to check whether the relationship is logically defensible. Now, a relationship is logically defensible if what we have seen, if what we have seen in one sample is what we shall see in other samples. Like now in this question, we dealt with 12 items and we got this equation. So if we were to go back to the same company and get some other set of data and get the same equation, then the data will be said to be defensible. The other one is whether the relationship is making economic sense. The relationship is said to make sense if what we expect is in agreement with what we have seen. So in our case here, we are going to test or we are going to confirm our variables are machine hours and so we are going to write this. So this is what we are writing because we already have the notes. So we are writing this. So our independent variable is machine hours. That is the independent variable. The dependent variable in this relationship, is electricity expense. Electricity expense. Now, what we need to do is to say the expected relationship. What kind of a relationship would you expect to exist between machine hours and electricity expense? Yesterday, I told you we have 3 types of relationships. We have the positive one, which we call direct And we said that this is where they are moving towards the same direction. We have the negative one, which we call inverse, and we say they move towards opposite directions. And then we have 0, which we call null, and we say they move towards opposite directions. Now, what kind of a relationship would you expect to see between machine hours and electricity expense? Let me see your response. Do you expect a direct, an inverse or no relationship? From your general knowledge, what do you expect? What do you expect? You have no idea what to expect.
I think a direct relationship.
Very good, Audrey. Here we expect a direct relationship. Positive. As we do more machine hours, or our machine runs more hours, we should incur more of electricity as we do more hours. So they are changing towards the same direction. Then we said that this one is now supposed to be observed. Observed relationship. Observed relationship, it is what now you have seen. It is what you have seen after you have run the equation. And what you have seen is reflected by the value of B. So we have seen a direct relationship. Why? We got a positive 12. Our value of B was 12. So the conclusion with that, the conclusion is that the relationship between machine hours, and electricity expense is economically plausible. It is making sense. It is making sense. Because what we expected is in agreement with what we saw. So we are not surprised. It is in order. You only get surprised when what you are expecting is different from what you are seeing. Like now, you are not surprised that you are in class because you expected to get me in class. And you expected yourself to be in class. And both of us now are in class. So it's making sense. So that is what we do when it comes to economic plausibility tests. When it comes to economic plausibility tests. So we move now to the next tests. We move to the next group. The next group Part B, they are called goodness of fit tests. Goodness of fit tests. Now these ones, they test how well the equation fits the data from which it was developed. How well the equation fits the data. It's the same thing we do when we go to a clothes store and you are buying clothes or you are buying shoes. You fit, you check whether the dress or the shirt or whatever is fitting you. And if it fits, you select it, you take it. If it does not fit, you don't select it. The same thing happens even with our relationships with one another. Brenda, make sure you mute yourself. Mute yourself, please. I was saying with our relationships, we test whether people fit. And if you find that someone does not fit, then you do not have anything to do with them. It's like what ladies will tell us men when a man approaches a lady, you quite often hear a lady saying or telling a man that you are not of my type. So as a man, when a lady tells you that you are not of her type, you should know that you do not fit. You are in different worlds. So there are six tests that are done. There are six tests that are done. And that is what I would want us to go through. Number one is called coefficient of determination. Coefficient of determination. Coefficient of determination, which is normally given as R squared. R squared. Now, this coefficient of determination, it shows us how well the equation explains how well the equation explains changes in y, or x explains changes in y. So in this case, we have the formula, which is already in your notes. And because the notes have the explanations, we will just go straight sum of y minus y predicted is square. You divide by, so this should be y minus y bar. Then sum of y minus y bar squared, you multiply by 100. You multiply by 100. So I want you to open where we had the table. Open where we had the table. We record those figures. So what are you getting? What are you getting from the figures? Okay, I'm expecting you to have this value y predicted minus y bar. Y predicted minus y bar squared, we got 277,776. Well, that is the formula. Maybe we can get the value. We can call it the value here. The value, but you can as well substitute straight. So the value is 277,776. You divide by y minus y bar. Y minus y bar, which is 347,122. 347,122 times 100. So when you do that, you should be able to tell me it is 277,776. You divide by 347,122 times 100. That is giving us around 80%. It's giving us around 80%. So the meaning of this, we are told to interpret this, the interpretation or the meaning, interpretation is that 80% of changes in electricity expense are explained or caused by changes in machine hours. So that is how we go about it. So that is the first test at the goodness of being test. Number two, the second one after this, as you can see in your notes, number two is called F-test. Now, F-test, it shows us the significance or the importance attached to the relationship. So it is done in several stages. like we did in hypothesis. I hope you are able to follow the notes on hypothesis. So in this one, we developed the hypothesis. And the hypothesis is developed like this. In the null, which we said we deny, you simply say the relationship is not significant. The relationship is not significant. That is how you design the null hypothesis. Then you come and do the alternative, which we say is designed to agree. To agree, where you would say the relationship is significant. The relationship is significant. Significant means it is important. You cannot ignore it. That's the meaning. You know, we have people that we have relationships with, many people, and some of them we easily ignore them. A good example is those fellows, when they call, you look at your phone, now you cannot stop what you are doing. You say, that person is not significant, or the relationship between you and them is not significant. But there's another guy who, when you see their call, you stop everything else that you are doing and attend to that call. That is a significant person or a significant relationship. So F is supposed to test that. So the first step is hypothesis, and this one you can cram it, it always remains that way. The second step, if you remember, it is called significance level. Significance level. Now, this is what I told you. We have the evidence of rejecting the relationship. So here, because the question has not told us, we will say let alpha to be 0.05. Let alpha to be 0.05. The next thing is called test statistic. Test statistic. Test statistic. Now, in test statistic, F is usually given as R squared to divide by K minus 1, which is divided by 1 minus R squared, which is divided by N minus K. N minus K. N minus K. So in this case, we compute something we call F calculated. F calculated is what you get when you substitute. So R square we have just found it is 0.8 or 80%. You divide by K. Now K, it is the computed parameters. So K here, it is our value of A and B. So they are just two. That's what we call K, the values that you have computed. We know that N is how many items we have. There were 12. There were 12. So I'm saying K represents the value we have computed, A and B. We computed those values in our equation. So there are 2, 1, 2. So K is 2. N is 12. So if I say so, then this will be 2 minus 1, which I shall use to divide by 1 minus 0.8. You divide this by 12 minus 2. You divide that. So when you do so, this is 1 minus 0.8. You divide by 10. Nick, I'm getting 40. Getting 40. So that is what you are also getting. When I get 40, I proceed now to the next step, which is called decision rule. Decision rule. Now, under this decision rule, first of all, we have something we call numerical degrees of freedom. Numerical degrees of freedom. The numerical degrees of freedom, they are this one, 2 minus 1. So 2 minus 1, which is 1. The numerator here. Then there is what we call denominator degrees of freedom. The denominator degrees of freedom. The denominator degrees of freedom is this one, 12 minus 2. And that is 10. 12 minus 2, and that is 10. Then we already know that our alpha is 0.05. Our alpha is 0.05. So our F critical at 1 and 10 at 0.05, our F critical with numerator degrees of freedom 1, denominator 10, and we are using the table of 0.05 is equal to. Now I want you to go to your tables, your tables huko mwisho, and check whether you can see a table that is written significance points of F. Significant points of F is on page 72, is table 4. Now, if you can see that table, you're here, you can see these ones that are on the top here, these are the numerator degrees, your numerator. Na hizi zimeteremuka hivi, they are the denominators. So what you do, you shall go to the numerator. Numerator is 1. So utasimama hapa kwa column 1. Then uteremuke kwa denominator. Denominator is 10. So tell me what you are getting. Type for me so that I see that we are together. What are you getting when you got column 1 and number 10 of the F tables? Yeah, good, Audrey. 4.96. So that is 4.96. Now with those items, yes, Collins, you can see that. You can draw a small diagram. You can draw a small diagram. Just illustrate, although it's not very necessary, it's not a must to draw. When you have this and you have this, we are good to go. So here, done like this, just like a small one. Now this is F critical. Crit is the short form for the word critical, which is 4.96. 4.96. Now this region here, it is a region where we will reject the null hypothesis. We will reject the null hypothesis. And if you find yourself here, we will accept the null. We will accept the null hypothesis. We will accept the null hypothesis. We will accept the null hypothesis. So having done that, we now proceed to the next step after the decision rule. The next step now is to make the conclusion. So the conclusion is done like this. You come and take the figure you had here, the 40. And as I told you the other day when you were in the confidence intervals, and also when we did the hypothesis test, you check where your calculated value is. So our calculated value is on the upper side because it's 4 and our calculated was 40 now. So we are in the region of rejecting. So we are going to say reject null hypothesis. Reject null hypothesis. Why? Since F calculated is greater than F critical. Is greater than F critical. That is 40 is greater than 4.96. So we are going to reject the null hypothesis since F calculated is greater than F critical. That is 40 is greater than 4.96. So if that is the position that we are taking, then what does that actually mean? What does that mean? So the meaning of that is that the relationship, remember we had two hypotheses here. The null was saying the relationship is not significant. So now we have said we reject null. So when you reject null, we are simply saying we accept, which we accept the alternative, which says the relationship is significant. So the relationship between machine hours and electricity expense is significant. The relationship between the machine hours and the electricity expense is significant. What that means is that you cannot easily ignore it. You cannot easily ignore that relationship is significant. It's very, very important. So that is number 2. Let's go to number 3. Under the goodness of fate. We are still under the goodness of fate tests. We are still under the goodness of fate tests. So we are computing something called standard error of estimate. Standard error of estimate. Now, this standard error of estimate is normally given as SE. And this is, it shows us the amount of error that is contained in the predicted value. The amount of error that is contained in the predicted value. So in this case, the formula for computing this, as you can see in your notes, the formula for the standard error of estimate, SE is given as sum of Y minus Y predicted. You square this, you divide by N minus K, then the whole of this, you get the square root. The whole of this, you get the square root. Y minus Y predicted, you square, then you divide by N minus K. That is the formula. The next thing is now to get the value. Is to get the value. Is to get the value. Now, in getting the value, in case you have any concern, because I've muted all of you, you can easily type. Value is where now you substitute, you say SE is equal to. So you go to the column that we had, this column that we called Y minus Y predicted squared, we got 73,090. 73,090. Now this one, if you divide by N, I've already said earlier on, it is 12, and K I've also said earlier on, it is 2. So when you get the square root of this, you will say 73,090 divided by 10, square root of the answer is 85.49. 85.49. So if that is the answer, 84.49, this value, we normally use it to get the confidence interval. Or the meaning of this, maybe I could interpret the meaning of this. The meaning of this is that the predicted value is expected to have an error of plus or minus 85.49. So when you use this equation to predict, like we were doing, the answer you get, it should have an error of 85.49. Now, as you can see in your notes, now this is what the examiner had asked. The examiner had asked this one. But now, this value, we normally use it to get the confidence interval. The confidence interval or confidence interval estimate. So the interval estimate, it is given as Y predicted plus or minus T 1 minus alpha out of 2 N minus K you multiply by SE N minus K you multiply by SE. So recall or remember that our Y predicted is 2 that 1. Our equation is 2 that 1 plus 12x. 2 that 1 plus 12x. So when x is 78,000 hours, when x is 78,000, I'm using the figure that is given in the question. The question, you look at your past papers, they have given that. Then y predicted will be 2 that 1 plus 12 times 78. Remember, our figures were in thousands, so you cannot bring this ikiwa full, because the figures, if you look at the figures we used, they were already in thousands. So this is then going to be 2 that 1 plus 12 times 78. That is 1167. 1167. So with that, we then come here and say t at 1 minus, before we say t, we are already told we test at what? Or the question has not mentioned there. The question has not mentioned the confidence interval. So we will have to design for ourselves. So we will say at 95% confidence level, at 95% confidence level. But if the examiner had wanted you to do this, they would have given you that percentage. So, t at 1 minus, I told you you use alpha is the value that remains for you to go to 0. So you divide it by 2 here. N, this is 12 minus 2 is going to be, go to your t tables. So when you go to the t tables there, when you go to the t tables, I told you the students tables. You come here where we have two-tailed confidence. Two-tailed confidence. And you go to where we have 95. So you stop at 95%. And then uteremuke kwa 10. So when you do that, check whether you get 2.2281. 2.2281. So if that is what you are getting, then we will come here and say then According to our formula here, we required the y predicted, which is 1167, plus or minus the value of t, which is 2.2281, multiplied by the standard error of estimate. You remember up there we have just gotten 85.49. 85.49. So proceeding on, you should be able to get 2.2281 times 85.49 is 190.48. 190.48. And as we say now, the lower limit will be 1167 minus 190.48. 1167 minus 198. No, 190. It's 190.48 is 976.52. 976.52. And then the upper limit will be 1167 plus 190.48. So if I say plus 190.48 times 2, getting 1357.48. 1357.48. And thus, I have 976.52. My predicted value should be between those two values. It should be between on the lower side. So when I have 78,000 hours or 78 hours, I am 95% sure. I am 95% sure that the electricity expense should be 1167. And if not that, it should be between 976 and 1357. That's what we call the confidence interval when we're using the standard error of estimate. Okay. Are we okay up to that point? If yes, type yes, I see. Yes, I can see Collins. The others, are we together? If you're not together, you raise the concern. Yeah, I can see Audrey, I can see Mwenda. Okay. So if we are okay, then I seek to proceed to number 4. Number 4 is called correlation coefficient. Correlation coefficient. Brackets R. Some people call it multiple R. Some people call it multiple R. Now this multiple R, as you can see in your notes, it is used to judge the type of the relationship and also the strength. The type and the strength of the relationship. So what we do, as usual, we begin with the formula. We begin with the formula here. Now R is simply given as the square root of R squared. We already have got an R squared. So the formula is like that. And the value is R calculated is simply the square root of 0.8. Because that is what we had gotten as R. So if you get square root of 0.8, I'm getting 0.89. 0.89. So if that is what you are getting, the meaning of this, the meaning of this value, the meaning of this is that there is a very strong direct relationship. You can quote this positive 0.89. You see it's positive, that means it's a direct relationship. And it's very close to 1. That's why we are saying very strong. Very strong. There is a very strong direct relationship between machine hours and electricity expense. Between machine hours and electricity expense. Machine hours and electricity expense. So that one is as simple as that. It is used to show us the type of the relationship and the strength of the relationship. And you compute it in a very simple way of getting the square root of R squared. There is a formula that we had used yesterday, and if you check that formula, there could be a slight difference. The slight difference, or the difference that you can see, is brought about by the fact that we decided to round up the figures. You remember I told you to round up the figures, we avoided the decimals. So those decimals are the ones responsible for the difference that you can see. But if we had used around 2-3 decimals, these figures should agree, figure to figure. Okay, so that is number 4. Let us do number 5. Let us do number 5, which is very clear in your notes there. Number 5. Number 5 is called standard error for the slope. For the slope. SB. Standard error for the slope, SB. Now this one, it shows the amount of error that is contained in the slope. It is also very, very simple. It's also very, very simple. And the formula for computing it is that SB is given as SE, which is divided by the square root of sum of x minus x bar. Sum of x minus x bar. That's how we get it. SE, you divide by the square root of sum of x minus x bar squared. So in this case, then, the value that you bring, the value is that SB, you remember what we got earlier on when we computed SE, it was 85.49. 85.49. Now this is supposed to be divided by the square root of, if you go to the table that we had drawn, our table, the column of x minus x bar, the total we got 1747. 1747. So if that is what we got, then we are going to say 85.49, you divide by the square root of 1747. I'm getting 2.05. 2.05. So the meaning of that, they are told to tell us what that means, is that the value of the slope, or the value for the slope, contains an error, of plus or minus 2.05. So the slope that we got, the value for B, when you look at it, you should expect to get a plus or minus 2.05. A plus or minus 2.05. Now in that case, they may ask you to get the confidence interval. They may ask you to get the confidence interval. The confidence interval. Now, if they want the confidence interval, the formula is B plus or minus T 1 minus alpha out of 2 n minus 1. So we are not now minusing k, it's 1. You multiply all that by SB. You multiply all that by SB. So we already know from our values that B is 12 from our computations. So at 95%, confidence interval, at 95% confidence interval, this T at 1 minus 0.05 out of 2. 12 minus 1. Someone to read for me and give me the figure. Let me see whether you are able to read that. The table that you have just read, this table of T. Give me the figure. I'm waiting for a figure from you. Hey, no one is responding. We said you got where there is 2. This is 2. So the 2-tail confidence, you stop at 95% because we are doing 95. Then uteremuke to where we have number 11. 12 minus 1 is 11. So if you do that, you should get 2.201. 2.201. That is what you're getting, 2.201. So if that is true, then I just proceed and say, then it will be 12 plus or minus 2.201 multiplied by SB. SB we have gotten here, 2.05. So this will be 12 plus or minus. If I take 2.201 times 2.05 is 4.5. 4.5. So if I say 12 minus 4.5, I'm getting 7.5. That will be my lower limit. And the upper limit then should be 16.5. And the upper limit should be 16.5. So that is how you get the confidence interval for the slope. The next one, number 6, test number 6. Test number 6. Test number 6. Test number 6 is called t-test. It's called t-test. That is test number 6. I hope you are still following your notes. So in this one, we begin with the hypothesis. It's a significance test. So we begin with the hypothesis. And the null hypothesis is stated that X is not a significant determinant of Y. That is how it's stated. X is not a significant determinant of Y. It's not a significant determinant of Y. And in the alternative, we say X is a significant determinant of Y. X is a significant determinant of Y. So that being true, we go to the next step, which we know is called significance level. Now the significance level, because the question has not provided, we assume, and when you assume, we say let alpha to be 0.05. We assume and rate it to be 0.05. Then we proceed and go to the third step, which is called test statistic. Test statistic. Now, test statistic, T is given as B. You divide by SB. So our T calculated will be our slope, which was 12. You divide by SB. SB, we had gotten 2.05. Remember, 2.05. So that gives us, if I take 12, I divide by 2.05, I am working with 5.85. 5.85. So after the test statistic, we now come and do what we call the decision rule. The decision rule. And if you followed our discussion on hypothesis, this one will be two tails. Two tails. It will be two tails. And if it will be two tails, the degrees of freedom. The degrees of freedom will be n minus 1, which we know is 12 minus 1, which is 11. The degrees of freedom will be n minus 1, which is 12 minus 1, which is 11. Which is 11. So with that, we come and design the table. We come and design the table for our rule, which will be like this. We have the lower side and the upper side. And wherever we find ourselves here, and inside here. Now, if we find ourselves inside here, we will say accept now. If we find ourselves below here, we will say reject now. And as well, if we find ourselves above here, we will as well say reject now. Now this one will be minus T critical, and this one will be positive T critical. And this one is exactly the same that we have read for B here at 95% and 11. The way tumekuja hapa tukasema two-tail confidence, unafika kwa 95, unateremka kwa number 11, which we have 2.201. So this is minus the 2.201, and this is positive 2.201. So if that is the case, then we come here and make our conclusion. We come and make our conclusion. And the conclusion is you compare this one, the calculated and the rule. You can see now equal more than 2. So we are going to reject null hypothesis. We reject null hypothesis since T calculated is greater than T critical. That is 5.85 is greater than 2.201. 5.85 is greater than 2.201. And if that is true, the meaning of that is machine hours. Remember, machine hours were our X. So machine hours are a significant determinant of electricity expense. Which is our Y. They are a significant determinant of electricity expense, which is our Y. So those are the tests that we have for the goodness of faith. Goodness of faith test. There are 6 of them. So I hope you follow them well. Finally, we now look at the third category. We said the test, the economic plausibility test, are 3 of them. The third category is C, which we call regression assumptions. Regression assumptions. Now, in this one, there is very little to write, because they are more of the observations. The assumptions are more of the observations, so there is almost nothing to write. So what I would like you to do is to follow the discussion, what is in the notes. There are 6 assumptions. There are 6 assumptions. Now, the first assumption is called linearity. And linearity simply says that the relationship between X and Y is linear. And that means it can produce straight lines when you plot it. So this one is tested in 2 ways. One is you plot the graph and you see whether it will give you a straight line. But in our case, we have not plotted the graph. But if you're using a computer, it can give you the graph, or you can plot by yourself. If you find that it is straight, that tells you it is linear. And not only on the positive, it could also be straight on the negative. It could also be straight on the negative. That is also linear. The other way of checking whether the relationship is linear is checking whether the equation you get takes the form of y is equals to a plus bx. And you realize that the equation we got was 2 plus 12x. So now that this one inafanana na hii, then we can say that this relationship that we are dealing with is linear. We can say that this relationship that you're dealing with is linear because what we got here was in conformity with what we should have gotten there. So that is called the assumption of linearity. It's as simple as that. Number two, it is called the zero mean of the error terms. The zero mean of the error terms. Now this one, it means that the error terms will have a mean of 0. As in, if you get all the errors, the errors are the ones we called, we divide by n, they are the ones we called y minus y predicted. You divide by n. If you look at this table that we drew, this table, because you already have it, now go to your table, you can see this column that we called error, this one. Now, the total here, and you can see it's plus or minus. The total is 22, negative 22. So if you are to get negative 22, you divide by 12. If you are to get negative 22, negative 22, you divide by 12. I'm getting something to do with negative 1.8. Now, this figure is too small when you compare with these other values of y. Hizi kina 1020, kina 820. And if we had not rounded, if you did not round, nakumbuka venye tuliround pale jana, if we had not rounded, this figure would almost have gone to 0. So in case you have not gotten a 0, although this is now about the syllabus, what we do, you subject this to a hypothesis test to confirm whether this is different from 0. But you can also use visual inspection. Visual inspection ni kutumia macho. Unasema hii 1.8 ni kidogo sana when it's compared to these figures. These figures, they are in thousands. So it is too small, so we can say it is 0. It's simple like that. The other thing is that the zero mean, the error terms, they are homoscedastic, or they are not changing, or they have what we call constant variation. Let me use that word as a little bit user-friendly. They are not depending on the values of x. And this one is done in a very simple way. You simply come to your table here, unaangalia these errors, whether they are changing as the value of x changes. You see this is minus 75, and the value of x is 72. Then we go to minus 71. So that means the error has reduced, which is the same case here. You can see from 72 to 55, we have reduced. Then the third value is 39, meaning x has increased. But the error here has reduced again. So you can see they are not changing in the same direction. They are not changing in the same direction. I hope you have gotten that. They are not changing in the same direction. So if they are not changing in the same direction, that means they have a constant variance, and they are good for regression. Just a minute. So, I was saying they are not changing in the same direction. The next thing that is number 4 is called normality. Normality for the error terms. And what that means is that these error terms should follow a normal probability distribution. And how we go about it, you take these error terms and you plot a graph. If it takes a shape like that, that is the normal curve. Remember we said normal curve has a mean of 0 and a standard deviation of 1. And it is divisible into 2 equal parts, 0.5, 0.5. So if you plot these ones and you find, if you plot and you find that they are giving you something like that, then we conclude they are following normal probability distribution. So again, we are not going to do all that. What the examiner is expecting of you here is just to appreciate the assumption and to know how it can be tested, but we are not going to test. The other thing is called autocorrelation. Autocorrelation. Autocorrelation has to do with the independence of the values of y. The values of y. And values are said to be autocorrelated if, when you know several of them, or the first 2, 3, you can tell the others. For example, if I told you the first value was 10, the other one was 13, the other one was 16, it is very clear that the other one should be 19, and the other one should be 21, and so on. Because in a car, we are just saying plus 3, plus 3, plus 3. So you only need to know the first few, and then you can generate the others by yourself. Sasa ukiangalia hizi values za y, you cannot say, unaona hii sasa ni 1020. Hii ni 1020, tumeenda kwa 820. So what has happened is like we have subtracted 200. So if this was autocorrelated, then I subtract another 200, I should have gotten 620. But what do I have? I do not have 620, but I have 720. So you can see they are not autocorrelated. Knowing of one does not help know the others. And that is good for the data. And the last assumption is called multicollinearity. Now, multicollinearity, it is used where we have more than one independent variables. For example, our equation was y equals to a plus b1 x1 plus b2 x2 plus b3 x3 and so on. So if you have more than one, we run a correlation coefficient matrix between these items here, where we have x1 here, x2 here, and x3, then x1 here, x2, and x3. Again, this could be slightly above your case. We check whether there is a correlation, whether they are influencing each other. It's just like what we do in the exam when we are checking whether candidates are influencing each other. So our question here does not have that case because it is single. Hatukuwa na more than one independent variables, so we cannot test. So that is all that you are supposed to do as far as the tests are concerned. Now, if you go back to the question that we had used, let's go now to the question. Let's take our past papers and see whether we have answered the question. Let's see whether we have answered. Remember, I said I was using the question for illustration. Using the question for illustration. So it's not every time utafanya hivyo. It depends on what you have been asked. So requirement number 1. Actually, now we can do the summary. We can even say summary solution. Summary solution for that question. Summary solution Part A, the examiner had said the least squares regression line for the above data and interpret the meaning. So equation we got y is equals to 2 that 1 plus 12x. 12 that 1 plus 12x. Now if we are told to interpret 2 that 1 is the fixed electricity expense. Electricity expense. Fixed electricity expense. The fixed electricity expense that does not depend on machine hours. That is the value of A. So it's the fixed electricity expense. It does not depend, it's not influenced by machine hours. Then this 12, it is the variable electricity expense. Electricity expense. Electricity expense per machine hour. Per machine hour. So for every machine hour, we are incurring 12 shillings. We are incurring 12 shillings. So the candidates should have produced, for you now to get this answer, for you to get that answer, you should have drawn this column 1, 2, 3, 4. So the first 4 columns were necessary for you to get that. Part B, the candidate had been told, estimate the amount of electricity expense. So this one we had said y predicted would be 2 that 1 plus 12 times 78. I think we had gotten that as 2 that 1 plus 12 times 78, 1167. That is what the candidate should have done. Number C, the product moment correlation coefficient between machine hours and electricity. So this is what we have called R. I think R we got, was it 0.89? We got 0.89 and we interpreted, so I'm not going to repeat the interpretation because we interpreted earlier. And D, the standard error of estimate. The standard error of estimate, SE. Now, SE, I think we had gotten 85.49. Now, for you to get to SE, then you require the entire table. You require the only column you did not require is this one of X, the last one. Yeah, so the question required the entire table to give those answers. So we are going to stop there. But as I told you, if you check your past papers, you will see almost every past paper has a question on this area. What we did yesterday and what we have done today. So almost every past paper has a question. So take time. First of all, revise what you have done yesterday and today. Familiarize yourself with them. Then go to the past papers, do some more. Yeah, because now we are through with that area. When we meet next, we shall have a new topic. I'm going to send the notes maybe later. Thank you.